Hi, so let's continue into a few more problems from Hamiltonian dynamics. Right, we'll do 3 problems. We'll actually solve 2 problems in this session, and 1 problem will be given as a practice problem. Right, just for you to get familiarized with some of the aspects of how we can, play around with these equations, how we can get equations of motion in different forms using the Hamilton's equation, etc. Right. So the first problem is this, right? The Hamiltonian of a particle of unit mass moving in the xy plane is given, right? The Hamiltonian is given here. Okay? And it said that the particle is moving in the xy plane. So there are 2 degrees of freedom in suitable units. The initial values are given to be, so we also are given the initial conditions, all right? So we need, when you try to solve the equations of motion, you need initial conditions, all right? The initial conditions are given here. The initial momentum and the initial position are given, all right? X of 0, y of 0, px of 0 and py of 0 are given. During the motion, the curves traced out by the particles in the xy plane and in the px-py planes are, all right? So we are asked to find the curves traced out in the, let's say, xy plane and in the px-py plane, all right? So we are not asked to find the curves traced out in the phase space. No, we are asked to find the curves traced out in the coordinate space and in the momentum space separately, right? We need to do this. Now, for example, when you need to find the curves traced out in the xy plane, right, you may need to find x as a function of y or y as a function of x. Similarly, if you want to find the curve traced out in the px-py plane, what you just need is px as a function of py or py as a function of px. Okay, this is what we need to find from the given Hamiltonian. Now, how do we do this? All right. So we know that once the Hamiltonian is given, we can get the equations of motion. How do we get the equations of motion? We can find x dot, which is dou h by dou px. We can find y dot. All right. We can find px dot. We know how to obtain py dot from the Hamiltonian. All right. Now these are differential equations. These are differential equations. So what we need to do is that we need to construct these differential equations, which are just Hamilton's equations. All right, these are the equations of motion, and then solve the differential equation, and then solve the differential equation. Okay. Now, when we try to solve the differential equation, you need to be careful here, because here they have asked us to find the trajectory in the xy plane, for example. All right, but when we find x dot and solve it, generally what you get is x of t. Am I right? We can construct this equation, x dot equal to dou h by dou px, or equations like that. All right, and you can actually solve this equation. When we solve this equation, from this equation, what you actually get is that solving this equation, what you actually get is x of t. Similarly, solving this equation, y dot equal to dou h by dou py, what you get is y of t. Similarly, from here we can get px of t, and from here py of t. All right. So these are the things we are going to find if we go on straight ahead. Now we look at what we are actually asked. We are not asked x of t or y of t. We are asked x as a function of y, or the trajectory in the xy plane, and px as a function of py. All right. Which means that from these two, you may have to eliminate one variable, which is t. Okay, that's the general way we proceed. All right. What you need to find is the trajectory in the xy plane. So from these two, okay, we have got x of t and y of t. So from these two, right, and how do we get this? We get this by solving these Hamilton's equations. Right. Now from these two, we eliminate the variable t to get x of y. Similarly, from these two, we eliminate the variable t to get px as a function of py. All right. Now we'll get the equation x of y, x as a function of y, and px as a function of py. All right. And looking at that equation, we shall be able to identify what kind of a curve it is, whether it's a circle, an ellipse, a hyperbola, or whatever it is. All right. So that's the general procedure that we need to follow in such problems. All right. So let's go ahead. Now with that introduction, we can get into the problem. What do we have here? We start with the Hamiltonian, of course. This is the Hamiltonian. Right? That's the given Hamiltonian. Right? From here, we know how to find x dot, the differential equation. X dot is dou h by dou px, and what's dou h by dou px? It's just x. So this is a simple equation. We have the differential equation x dot equal to x, which means that this is the differential equation dx by dt is equal to x. That's dx by dt is equal to x. Alright, now we can actually solve this differential equation. So when we try to solve this, there are different ways to do this. Alright, maybe we can eliminate time at this stage itself, or we can solve the equations from here. You could proceed in any way. Alright, so the way we proceed here, we'll solve this equation first. We'll solve this differential equation first. Alright, so we are given dx by dt is equal to x. Okay, and x of 0 is given to be 1, if I am right. See, x of 0 is equal to 1. Okay, so when we integrate, we have dx by dt is equal to x. Alright, so this means that we can separate the variables. We have got dx by dt is equal to x. We can separate the variables and we have dx by x is equal to dt. Now you can integrate this. Alright, from t equal to 0 to sometime t. Alright, then you can find the initial conditions by at t equal to 0, the initial position is given, the initial value of x is given as 1. So you can integrate it as integral 1 to x. Alright, this is a technique that you can use. Alright, or what you can do is that you could do the indefinite integral and then find the constant of integration. Alright, so this part I will do in this way, because the initial condition is already incorporated here. Alright, this would give you the same result. Or you could actually do the indefinite integral without these limits and then find the constant of integration using the initial conditions. Alright, both these methods are equivalent. Okay, I hope that's clear. For example, the px/py part, we'll do it by finding the constant of integration, just so that you get familiarized with both these methods. Okay, so from here you see that integral dx by x is log x. Obviously, it's log x from 1 to x, right, is equal to t. Log x is equal to t. So log 1 is 0, so that gives you log x is equal to t, or x is equal to e raised to t. X is equal to e raised to t. That's our solution. We have got x of t. We have found x of t. Okay, in exactly the same way we can find y of t, because y dot is equal to dou h by dou py, which is equal to minus y. Y dot is equal to minus y. You solve the equation in exactly the same way. Because of this minus sign here, you get y is equal to e raised to minus t. Alright, so you've got x of t and y of t. Alright, what we need is x as a function of y, something like that. Alright, so for that you need to eliminate t, the variable time, the time variable, from these two equations. Now here, looking at this, you see that there's an easy way of eliminating these variables. Alright, sometimes, in some cases we need to divide x of t by y of t, sometimes you may need to multiply, whatever. Here what we see is that you can just divide x of t by y of t. No, you have to multiply them, because it's e raised to t and e raised to minus t. So you see that x multiplied by y is equal to 1. Right? Xy is a constant, which means that you found x as a function of y. Alright, x of y is equal to 1 by y, x is equal to 1 by y, something like that. Alright, but it's more enlightening in this form. Xy is equal to 1. Now this is an equation for a particular kind of curve. Xy is equal to constant. Xy is equal to constant. Okay. Alright, xy is equal to constant. This is an equation. If you can go and check, xy is equal to constant, it corresponds to a class of hyperbola. It's actually equation for a rectangular hyperbola. Rectangular hyperbola. Alright, xy is equal to 1. Alright, this means that the product remains a constant. The product remains a constant. Let's just try this. Alright, y and x. Okay, so when x is 1, when x is 1, let me just draw it straight. Okay, you should be able to identify that this is a rectangular hyperbola. If not, you look at this. Alright, you can just try plotting this. Xy is equal to 1. You have got a y, x here. Let's say this is x equal to 1, x equal to 2, x equal to 3, etc. Okay, so this is 1, 2, etc. So when x equal to 1, y also has to be equal to 1, right? I think we should make it a little bit more resolved. Let's draw the xy plane like this. Okay, so this is 1, so this should be 0.5, and this is 2, So this should be 1.5, etc. Here you have got 0.5, 1, like that. All right. So when x equal to 1, we know that y is equal to 1. When x equal to 1, y is equal to 1, because then xy is equal to 1. All right. What happens when x equal to 2? When x equal to 2, y is equal to 0.5, then xy is again 1. Okay. So you see that you can plot it in this way, and you see that it will belong to what you call as a rectangular hyperbola. It will be a rectangular hyperbola, which means that as x increases, y should decrease, and vice versa. As y increases, x should decrease. Okay. So by looking at this, okay, you could actually plot a few more points if you are not convinced, and check whether this has the form of a rectangular hyperbola. You will see that this xy is equal to constant is a rectangular hyperbola. Now with that, we can actually look back at the options. All right. So the first option says both are straight lines, the second a straight line and a hyperbola respectively, the hyperbola and ellipse respectively, both hyperbolas. All right. So we cannot completely find, all right, because the option says that the first one is definitely not a straight line, so we can actually exclude A and B. It could either be C or D. So we don't have enough information to choose the correct option. So let's go back and find Px, Py. So from the Hamilton's equation, we can see that Px dot is equal to minus dou h by dou x, okay, which is minus Px plus x. Right? Why? Because you look at the Hamiltonian here and you find dou h by dou x, and you see that it's equal to Px minus x. Right? It's Px minus x. Fine. So this means that Px dot is equal to minus Px plus x. That's exactly what we have written here. Okay. Px dot equal to minus Px plus x. Alright, fine. Now this means that we have got this differential equation dpx by dt plus px is equal to x. Okay, and we have already found x is equal to e raised to t. Okay, we have substituted x is equal to e raised to t here. We get this differential equation. Okay, now you must already be familiar with solving these kinds of differential equations. Alright, these are the types of differential equations which can be solved by multiplying throughout by an integration factor. Because then we can write this equation as a total derivative of something, a total derivative of a product by introducing a integration factor. Okay, so that integration factor thing, I assume you are already familiar how to find the integration factor, etc. Okay, for example, if you have an equation of this form, dy by dx plus some function p of x multiplied by y is equal to q of x. Okay, if the differential equation is of this form, then you know that the integration factor is e raised to integral p of x dx. That's integration factor. Okay, so here in place of y you have px. Okay, and in place of p of x here you have got 1. So what's the integration factor here? Integration factor is e raised to integral dt, because instead of x here, right, in the place of x here, what you have here is t. Okay, so if you make this observation, you know that the integration factor is e raised to integral dt, which is e raised to t. Okay? So you multiply this throughout by e raised to t. Yeah, so that becomes e raised to t dpx by dt plus e raised to t px is equal to e raised to 2t. Okay, now what does this mean? Right, this means that we can write this as a total derivative. Let me write it here. This means that d by dt of e raised to t px is equal to e raised to 2t. Right, because if you take the derivative of this, all right, if you use the product rule, you see that the first term would be okay, if you use the product rule, if keep e raised to t, then dpx by dt. All right, that's this term, and then you take the derivative of e raised to t and retain this px. That's the product rule. Right, that will give you this term. Right. Now we have got the total derivative is something. So now it's easy to solve. Okay, now it's easy to solve because the total derivative of something is equal to e raised to 2t. This means that e raised to t px, okay, yeah, e raised to t px, because if you integrate on both sides, here this differentiation just disappears. All right, what you have here is e raised to 2t dt, integral e raised to 2t dt. Okay, and then there should be a constant of integration which has to be found using the initial conditions. All right, that's exactly what we have done here. Now if you integrate this, it's equal to e raised to 2t by 2. Okay, so px et is equal to e raised to 2t divided by 2 plus the integration constant c1. All right, this integration is not particularly difficult because it's an integral of e raised to 2t, which is simply e raised to 2t divided by 2. Right, so we get this equation. Okay, and maybe we can go one more step and say that px of t is equal to, from here we can find px of t is equal to, you just multiply throughout by e raised to minus t, that becomes e raised to t by 2 plus c1 e raised to minus t. Okay, fine. Or we can retain it in this form, it doesn't matter. Similarly, in exactly the same way you find py dot. Okay, py dot is minus dou x by dou y, which is py plus y. This means the equation is dpy by dt minus py is equal to y. And what's y? Y we have already found to be e raised to minus t. Okay. Now again you can use the integration factor idea here and you get this and then you integrate it. Right? It's exactly the same method that we did before. So it's py e raised to minus 2 e raised to minus t is equal to minus 1 by 2 e raised to minus 2t plus c2. Okay. It's all fine. Now we need to fix this c1 and c2. So you look at the initial conditions. Okay, what's the initial condition given? Px of 0 is 1 by 2. Am I right? Px of 0 is 1 by 2. Px of 0 is 1 by 2. So you put t equal to 0. Okay, t equal to 0. This means that px of 0 at 0 is it's 1 by 2. E raised to 0 is 1. So it's equal to 1 by 2 plus c1. This means that c1 is equal to 0. All right. Again, you can find c2 is also equal to 0 in exactly the same way, because here py of 0 is given to be minus 1 by 2. Right. So in exactly the same way, you will find that c1 and c2 are equal to 0. Fine. Now we have got px is equal to 1 by 2 e raised to t and py is equal to minus 1 by 2 e raised to minus t. Right. Now we need to eliminate t from this, because what we need is the curve in the px py plane, which means that what you need is a function px as a function of py or py as a function of px. So you look at this, how do we eliminate the variable term? It's easy, you just multiply them. Okay. So you see that px py is equal to 1 by 4 or minus 1 by 4, sorry. Px py is equal to minus 1 by 4. The time is eliminated, you have obtained px as a function of py or py as a function of px. If you look at this, it's exactly the same form as xy is equal to constant. All right, we have got px py is equal to a constant. All right, this is also an equation for a rectangular hyperbola. It's a class of hyperbolae. All right, so we have found that both in the xy plane and in the px py plane, we have got the curve. The curves are hyperbola corresponding to a rectangular hyperbola corresponding to the given Hamiltonian. All right, so we have solved the problem. The correct answer is option D. Both are hyperbolas. All right. Now, I've explained every step along this way, and in your exam, you should be able to do it in a much quicker pace. All right, so you need to be familiar, quite quick with solving differential equations, etc., which I hope by now you have some practice with. Okay, let's go on to the next problem, which also was asked for one of the previous examinations. All right. The Hamiltonian of a relativistic particle of rest mass m and momentum p is given by h equal to square root of p square plus m square plus v of x. Okay, in units in which the speed of light c is equal to 1. All right. So we are given the Hamiltonian of a relativistic system here. The Hamiltonian of a relativistic system here. Now it's a good thing to observe at this point that this is exactly the total energy of a relativistic particle, right? Because you know that E is equal to p square c square, sorry, E is equal to square root of p square c square plus m square c raised to 4. So in the units where c is equal to 1, this becomes E is equal to square root of p square plus m square. Okay. So from here you see that the relativistic Hamiltonian is exactly for a free particle. right? It's exactly the relativistic energy. And then if there's a potential, then it's just plus V of x, right? So for a relativistic particle, the Hamiltonian is just the total energy. It's all fine. The Hamiltonian is just the total energy. That's what is given here, right? We need to find the Lagrangian. We need to find the Lagrangian. All right. So how do we find the Lagrangian? First of all, you have to remember that the Lagrangian has to be a function of x dot x and t generally. All right. There may not be a t there, but generally it's a function of x dot x and t. There shouldn't be any p in there. So we should eliminate the p in favor of x dot when you go to Lagrangian. Right. So let's just do the traditional way. Let's just follow the steps. It's just a one-dimensional system here. Okay. We have got just one momentum p. Okay, and we have got just one. We have got just one coordinate x. Okay, and if you look at the options, there are one x dot and x, x dot and x, x dot and x. So we just need one coordinate. All right. Lagrangian is x dot p minus h. Fine. How do you find h dot? Sorry, how do you find x dot? We know that x dot is equal to dou h by dou p. Am I right? So what's that? You just take the derivative with respect to p. You see that it's 1 by 2 square root of p square plus m square multiplied by 2p, all right, which is the derivative of p square. Okay, so this is 2p divided by, so this is just x dot is p divided by square root of p square plus m square. Okay, and in our final formulation we don't need any p there. Okay, so you see that you can use this. All right, you can use this to, so what's x dot p here? So if you look, the Lagrangian is x dot p minus h, so that's equal to p square divided by square root of p square plus m square minus h. This is the Lagrangian, right? But now this Lagrangian here. Okay, so let's write the Hamiltonian here. Hamiltonian is square root of p square plus m square minus v of x, all right? But now this is a function of p and x. What we need is a function of x dot and x, right? So let's see how we can do that. So how do we make a simple substitution here? Let's look at that. So yeah, from here we can solve for p in terms of x dot, right? From here we can solve p in terms of x dot, right? So this is the intermediate answer. We need to make the correct substitution now. Let's see here. So you see that x dot is p by square root of p square plus m square. So this, from here you can solve for x dot. Okay, just square these things. So you see that p square is equal to m square x dot square divided by 1 minus x dot square. How do we do this? Again, I'll just give you one more step. You see that x dot square is equal to p square divided by p square plus m square. Okay, so from here you see that p square is equal to p square x dot square plus m square x dot square. Okay, so from here you see that p square multiplied by 1 minus x dot square is equal to m square x dot square, or p square is equal to m square x dot square divided by square x dot square divided by 1 minus x dot square, or p is equal to m x dot divided by 1 minus x dot square. Now you might be able to identify this thing. What we have found is that p is equal to m x dot divided by 1 minus x dot square root of, right? What is this actually? Okay, you must already be familiar with the relativistic momentum. P is equal to gamma mv, right? Gamma, what's gamma? Gamma is 1 by square root of 1 minus v square by c square. So it's mv divided by square root of 1 minus v square by c square. We have got m is equal to, so this is mv divided by square root of 1 minus v square by c square. This is the relativistic expression for the momentum. This is the relativistic momentum. Okay, there's a gamma factor here. It's not exactly the Newtonian momentum, which is mv. Here we have got mv divided by square root of 1 minus v square by c square. Okay, when c is 1, we have got mv divided by square root of 1 minus v square. That's exactly what we have here. Okay, p is equal to mx dot divided by square root of 1 minus x dot square. Right. So we see that by choosing the Hamiltonian in this way, by choosing the Hamiltonian as the total energy, we automatically see that the conjugate momentum is the usual expression for the relativistic momentum of the particle. So this is a good thing to start with. Okay, but if you look at this thing, what we have here everywhere is p square plus m square, p square plus m square. Let's find p square plus m square from here. Okay. So let's substitute p square plus m square. You see that p square plus m square is just add m square. All right, just add m square here, and you see that p square plus m square is equal to m square divided by 1 minus x dot square. All right. Now you can substitute all this back in here. You can substitute all this back in here and obtain the final answer. Okay. So we substituted, this is x dot and this is px, this is x dot px, right, or x dot p. Okay, I have substituted here, we have found p, so we can find x dot p. P is mx dot divided by square root of 1 minus x dot square minus, and what do we have here? We have got square root of p square plus m square. Okay, so square root of p square plus m square, from here you see that square root of p square by m square is m divided by square root of 1 minus x dot square. This is square root of this. Okay, we just take the square root of this. Okay, you could substitute in any which way you like, but this seems to be the simplest step to take. All right, so you write the relativistic momentum which you obtained from here. All right, which you obtained from here. You invert this and find p as a function of x dot. Substitute that here. Okay, minus m divided by square root of 1 minus x dot square minus v of x. Fine. Okay, now it's just a matter of simplifying this, and you see that. Okay, simplify this. Right, it's just one step, and the final answer is it's minus m square root of 1 minus x dot square minus v of x. All right, so this is the relativistic Lagrangian for a particle in a potential v. Okay, now this looks a bit surprising. You see that it's no more of the form t minus v. No, it's not more of the form t minus v. All right, the Hamiltonian in this case is of the form t plus v, but the Lagrangian is not of the form t minus v. All right, so the form of the Lagrangian t minus v that we are quite used to, it's only applicable for a few problems. All right, so it's not a very general result, but most of the problems that we do during our course involves problems where the Lagrangian is L is equal to t minus v. You see that it's not the case here. Okay, it's minus m square root of 1 minus x dot square minus v of x. Okay, that's Lagrangian. Do we have it in our options? Yes, yes, this is the Lagrangian. All right. Okay, there are other ways of arguing that this has to be the correct Lagrangian. We don't have to go into the details. Maybe when we discuss the special theory of relativity, will explain why this has to be the form of the Lagrangian. Okay. All right. You can actually obtain this Lagrangian by demanding that the action is actually Lorentz invariant. All right, we have got this action, and we know that if your equations of motion needs some symmetry, you just have to make the action symmetric. All right, if your equations of motion needs to be symmetric, you just make the action symmetric. Okay, and then the equations of motion will automatically become symmetrical, right? So in special theory of relativity, the fundamental symmetry is Lorentz transformation symmetry, which means that the equations of motion should not change when you make a Lorentz transformation or when you go from one inertial frame to another. Okay, so by demanding that the action is actually relativistically invariant, you can make sure that the equations of motion are also invariant under Lorentz transformations. Okay, that's exactly the point we'll use to obtain this result for the Lagrangian. Okay, but we'll come to that in a later stage. At this point, we can just solve it as a problem, even if you don't know the details. Okay, even if you don't know the details, you know that if the Hamiltonian is given in this form, you know exactly how to find the Lagrangian. All right, you don't have to know all these details. If the Hamiltonian is given, you know how to find the Lagrangian. Okay, that's exactly what we have done here. Okay, all right. Now, there is one more problem that's left as a practice problem, all right, and I've given the steps. You can go through that. If you have any doubt, you please contact me. Okay. So the question is, describe the motion of a particle of mass m constrained to move on the surface of a cylinder of radius a and attracted towards the origin by a force which is proportional to the distance of the particle from the origin. We have got a force which is of this form, all right, F equal to minus kr. Okay, and you see that this force you are already familiar with from the harmonic oscillator. Okay, but you can solve this problem using the Hamiltonian method. Okay, you could also do the Lagrangian method, which you are familiar with. So I think I can give it to you as an exercise to work on this problem using the Lagrangian and the Hamiltonian approaches. Okay, so you will see that the Hamiltonian approach doesn't necessarily make the problem simpler. Okay, but you need to get some practice with this Hamiltonian thing. Okay. With that, I think we have covered all the necessary theory and the problems, the types of problems that might be asked for the examinations from the Hamiltonian viewpoint. Okay. The next thing we need to introduce, which is also very important from the examination point of view, is the Poisson bracket, which we'll do in the next class. Let's do that in the next class. Okay. Thank you.